The next talk is by Antonio Pereira from Radboud University and Fluminense Federal University in Brazil. Antonio will speak about the fixing the gauge fixing procedure, okay, in a non-perturbative concern. Please, Antonio, the floor is yours.
Thank you, Joseph, for the introduction, and thank you to the organizers for the invitation. I hope that you can hear me well. So unfortunately, I could not be there in person because I had an emergency, and I was in the Netherlands, and I had to come back to Brazil. So it was a big, well, it was hard to synchronize things in such a way that I could be there on time. But in any case, I was talking to Johannes about the diversity of the audience, and I decided to talk about a research line that I have been doing over the past 10 years, which is the non-perturbative improvement of the gauge fixing procedure. So let me start by mentioning that I'm going to summarize, or at least speak very roughly about work that is in progress since 2013 with all these different collaborators. And the outline is such that I will introduce the problem that makes us concerned about the gauge fixing procedure in the non-perturbative regime of gauge theories. So I will focus in ingenious theories throughout my talk, but I'll also try to make brief comments about quantum gravity in the end. But the problem is known. I mean, is the so-called Gribov problem. And I will try to present to you the ways that myself and collaborators are trying to deal with this problem in practice and obtain concrete results. So let me just start with a very general introduction that, well, of course, we don't have a full analytical understanding of non-perturbative ingenious, and of course, we want to understand this regime of these theories because this will provide an understanding of the mechanism that drives confinement, color confinement of quarks and gluons. And there are many non-perturbative approaches, in particular functional methods, Dyson-Schwinger equations, functional renormalization group that you have heard about in this workshop, lattice calculations, effective models, well, holographic techniques, and so on. And all these approaches, they are able to give us pieces of information of non-perturbative ingenious, but we still don't have a complete picture of what is going on when the theory becomes strongly coupled. And of course, ingenious theories are invariant under the gauge transformations, and this means that for a given field configuration A mu, there are infinitely many equivalent configurations that are connected to it by gauge transformations. And when we approach these theories in the continuum, namely you treat space-time as a continuum, one practical way is to deal with this redundancy is to use the gauge fixing procedure. And when we formulate ingenious theories through the path integral, the very standard way is to use the so-called Faddeev-Popov procedure. And we know that this procedure gives good results in perturbation theory. And this is the standard way of proceeding with ingenious theories when you do perturbative calculations for gauge invariant observables and you can compare and compute scattering amplitudes and so on. A toy model of the Faddeev-Popov procedure can be illustrated by considering a real function, f of x, that has n roots, xy up to xn. And we can formally write this identity that you take the Dirac delta functional composed with this function f. And this is equivalent to the sum of these delta functions divided by the derivative of the function of f computed at those roots. And when you write this identity, of course, you assume that this derivative exists. And when computed at the roots xi, this derivative is non-vanishing. And if you integrate this expression, then you collapse these delta functions here on the right-hand side. And on the right-hand side, you just get this sum over f prime of xi. And you can just take the sum, put to the left-hand side, and you get this identity. And it is precisely this identity that is at the core of the Faddeev-Popov procedure. You insert 1 in your path integral, and you rewrite it as this sum. As this relation. Now, if you view this f of x as the analog of the gauge fixing condition, then we expect that this function has just one solution, x tilde one root x tilde per gauge orbit. And we also, that there is a second assumption in the Faddeev-Popov procedure that is less appreciated, which is that we assume that this derivative it exists, it is non-vanishing, and it is positive. And if you do this this second assumption, if you take this assumption seriously, then this identity can be written in this form. And this is precisely the Faddeev-Popov trick that we see in textbooks, where f prime corresponds to the Faddeev-Popov determinant, and the Dirac of f of x is precisely the Dirac delta functional that imposes the gauge fixing condition. Okay. If you go to the functional form, then this is the expression. So you have your partition functional. I'll be working in Euclidean signature, and I'll also use as a gauge group SUN throughout this presentation. And the gauge fixing condition is, I'll call it f of functional of A equals to 0. And the gauge fixing now is implemented by inserting the identity that comes from this Dirac delta function, the Faddeev-Popov determinant, and the integration over the group elements. And as I said, just to re-emphasize, when I write this expression, I'm assuming that f of A equals to 0 has a unique solution per gauge orbit. And this Faddeev-Popov determinant does not vanish. And moreover, in the Faddeev-Popov procedure, I'm assuming that it is positive. And then we can just remove this absolute value that enters here. So this is the standard way that we see in textbooks. And now that we have worked out the general form of the Faddeev-Popov procedure, we can just work with a concrete gauge fixing condition and see if these assumptions are justified. And what we do is to choose the Landau gauge. And the Landau gauge is given by the divergence of A mu equals to 0. And we can check whether it picks one representative per gauge orbit and if the Faddeev-Popov determinant does not vanish and is positive. And it turns out that if you pick a configuration A mu that satisfies the gauge fixing condition, and you pick a second gauge field configuration A prime that is related to by a gauge transformation, but also satisfies the gauge condition, you can ask yourself if such a configuration A prime it exists or is just a trivial solution. And what I'm going to do is to take the particular case of an infinitesimal gauge transformation. So A prime is related by this shift with the covariant derivative acting on the gauge parameter. And you see that if A prime satisfies the gauge condition as well, then I can rewrite A prime as A minus covariant derivative. And since A also satisfies the gauge condition, I end up with the condition that this operator, which is nothing but the Faddeev-Popov operator, must have a zero mode. So if A and so the summary is if A and A prime both satisfies the gauge condition and are related by an infinitesimal gauge transformation, then the gauge parameter psi must be a zero mode of the Faddeev-Popov operator. So now we can just ask ourselves if this operator minus d, partial d, and covariant derivative, it really has zero modes. And as I said, the condition that we use in the Faddeev-Popov procedure is even stronger. We assume that this operator is positive, so that we can lift the determinant to the exponential using the standard Faddeev-Popov ghosts. So it turns out, and that's the main contribution that Gribov gave in '78 in terms of realizing that actually this operator has zero modes. And this means that since this operator has zero modes, the Landau gauge condition is not ideal in the sense that it does not pick just one representative per gauge orbit. So even after gauge fixing, we still have some residual gauge freedom. And of course, the presence of zero modes makes the Faddeev-Popov procedure ill-defined. And those configurations that are connected by gauge transformations and are related these configurations that satisfy the gauge condition and are related by gauge transformations, they are called Gribov copies, and their existence is precisely what we call as the Gribov problem. So in order to implement the Faddeev-Popov procedure, we have to remove these copies as well. And just to understand why we use the Faddeev-Popov procedure in perturbation theory, and this gives a concrete framework to do, let's say, consistent calculations, we can expand the Faddeev-Popov operator in terms of, you can expand the covariant derivative that appears in the Faddeev-Popov operator, and you see that it is separated in two parts. One part, which in Euclidean space is strictly positive, which is this one, plus the second one, which in perturbation theory, where we assume that the product of the coupling constant G and the field A is sufficiently small, this means that this term here is sufficiently small compared to this one. So this means that in perturbation theory, the first term dominates, and therefore the condition that this operator is positive is satisfied. So the assumption of having a positive Faddeev-Popov operator is ensured in perturbation theory. And since it is positive, you also don't have zero modes, and consequently, you don't have infinitesimal Gribov copies. However, if you want to do non-perturbative calculations, so if you want to take this product of G and A bigger and bigger, then this term can really dominate over this term. And eventually, you're going to have a zero mode and even flip the sign of the operator. So this suggests that these Gribov copies, they are irrelevant in the perturbative regime, but they can play some role in the non-perturbative regime. So we want to improve the Faddeev-Popov procedure in such a way that when you do non-perturbative calculations, you still get a consistent framework. So you can visualize this perturbative / non-perturbative discussion by taking a configuration space and taking gauge orbits by being represented by these dashed lines. And you see that this section here is the gauge fixing section. And when you do perturbation theory, essentially you take field configurations around the trivial vacuum, and you see that locally you can trace a section in your fiber bundle in such a way that you just cross each gauge orbit once. But as soon as you go to non-perturbative configurations, that you are going to look at this field space in full glory, then you see that you are going to cross the same gauge orbit more than once, and these are precisely the Gribov copies. Okay. Up to now, I just talked about infinitesimal Gribov copies. This is not the full story. We also have copies that are generated by finite gauge transformations, as identified by Van Baal in 92. But dealing with those copies is still an open problem. And therefore, I will just try to deal with infinitesimal Gribov copies. But the infinitesimal Gribov copies, they are particularly important because they are also those that make the Faddeev-Popov determinant, the Faddeev-Popov operator having zero modes. And therefore, they seem to be the most important ones. But this is just a speculation that I'm doing. Also, let me say that in the same year that Gribov published his paper, Singer proved in a mathematically rigorous way that these Gribov copies, they are not a particular problem of the Landau gauge, but actually of all continuous gauge fixing conditions in field space. And the origin of the problem is a geometric one. So we were trying to trace a global section over a non-trivial fiber bundle. And although the very existence of the Gribov problem is a characteristic of non-abelian gauge theories, the way that you handle Gribov copies depends on the choice of the gauge. So what I'm going to do now is to stick to Landau gauge, try to deal with the problem in Landau gauge, and see what is general in this discussion that can be extrapolated to more general gauges. So Gribov himself proposed a way to deal with those copies, and the proposal was the following. So he proposed to restrict the path integral to a region omega, which is free of infinitesimal Gribov copies. And this region is defined by precisely the region where the Faddeev-Popov operator is positive. And this region has all the nice properties in the sense that it is a bounded region. All gauge orbits cross this region at least once, because you still have Gribov copies that are related by finite transformations. But in principle now, you can just restrict your path integral to this region in such a way that you avoid the zero modes of the Faddeev-Popov operator. And let me emphasize again that this region is not free of all Gribov copies, but just infinitesimal ones. And since this region is bounded in every direction in field space, the boundary of this region is what we call the Gribov horizon. And it's precisely at the horizon that the first Gribov copies are appears. So in practice, what you do, you have your partition function, and you insert this V of omega, which will play the role of restricting the path integral to the Gribov region. And in your Boltzmann weight, you have the gauge fixed Yang-Mills action in Landau gauge. And this is expressed here. And you see that I'm imposing the Landau gauge, and here I have the Faddeev-Popov term with the Faddeev-Popov ghosts. And a practical way of implementing this restriction to omega is to demand that the two-point function of the Faddeev-Popov ghosts, with considering A, the gluon, as an external field, is simply the inverse of this operator. And since we want to avoid zero modes of this operator, the equivalent requirement is to impose that the two-point function of the Faddeev-Popov ghosts has no poles besides the trivial and standard pole p squared equals to 0. And imposing that is the so-called no-pole condition. And this is what Gribov did at leading order in his work. So he expanded the ghost two-point function at leading order. So when you have two insertions of the gauge field, and demanded that this two-point function has no poles. Later on, 10 years after, Daniel Zwanziger generalized these restrictions to all orders, so with infinitely many insertions of gauge fields. But he did that in a different way, so he didn't use precisely the no-pole condition, but an equivalent condition. And much more recently, it was proved that extending Gribov's prescription to all orders is equivalent to Zwanziger's prescription. And the outcome of this procedure is that that V of omega can be lifted to the Boltzmann weight. And so besides the standard gauge fixed Yang-Mills action, you now have this term plus a volume term. And this term, H of A, is what is called the horizon function. And it essentially contains two gauge fields with the insertion of the inverse of the Faddeev-Popov operator. So intuitively, when the Faddeev-Popov operator hits a zero mode, this term will blows up and will simply suppress the partition function. So this is a highly non-local function because this is the inverse of the Faddeev-Popov operator. And this parameter that appears, gamma, is what is called the Gribov parameter. And it's not a free parameter, but rather it is fixed by a gap equation. So you have to impose that the expectation value of the horizon function actually is a volume, this volume of, well, it's space-time dimensionality times the volume of space-time times the volume of the gauge group. Sorry, not the volume. Yeah, well, it's n squared minus 1 for SUN. And this means that the resulting action that dynamically implements the restriction to the Gribov region is a non-local action. But of course, there is a remarkable feature in this case that the Gribov-Zwanziger action can be cast in a local form by introducing auxiliary fields. So if you introduce a pair of commuting fields and anti-commuting fields in the bi-adjoint representation of the gauge group, you can write the Gribov-Zwanziger action as the standard gauge fixed Yang-Mills action plus this term, which contains the auxiliary fields. So you see that these terms here, they are some sort of, well, supersymmetric related, if you think of this as commuting and this anti-commuting. So you have precisely a supersymmetry that transforms phi to omega. And you have the second, this third term, sorry, that contains explicitly the Gribov parameter. And now the gap equation that fixes gamma is just the minimization of the vacuum energy, and it gains this form. So you have the expectation value of A times these auxiliary fields, and these must be a non-vanishing quantity. And this is how you fix gamma. Another remarkable feature is that this action is renormalizable at all orders in perturbation theory, as proved by Zwanziger. So you have a local theory, an action that is renormalizable, and now that effectively implements the restriction to the Gribov region, and now you can do concrete calculations. Some comments about the Gribov parameter, which is, as I said, is not a free parameter. So if you solve this gap equation to some extent, I mean, in an approximation, you see that it has this non-perturbative feature that when G is small, then well, in the ultraviolet, when G goes to 0, then also gamma goes to 0, and you recover the standard Yang-Mills action. And when G grows, when you go to the non-perturbative regime, then gamma is not negligible. So the Gribov parameter, it encodes this restriction to the Gribov region. And of course, I mean, you can interpret this as being related to this boundary that was introduced in field space that is precisely the Gribov horizon. So now, for instance, with this modified action, you can compute the tree-level gluon propagator. And this propagator is very different from the perturbative one, which is just 1 over k squared. And you see that this propagator, when k goes to 0, instead of diverging as the perturbative propagator, it goes to 0 exactly. And so this drastic change in the gluon propagator behavior was explored over the last 2 decades, and for many, many years, lattice calculations were really seeing the propagator going to 0. So this was really a nice scenario that could explain this dynamically. And there is a fact that this propagator with this bump, so it starts with 0, there is a bump, and then goes to 0 again. It violates reflection positivity, and therefore gluons cannot be interpreted as excitations in the physical spectrum of the theory, and people have interpreted that as a signal of confinement. But of course, keep in mind that the propagator is a gauge-dependent quantity, so we have to be careful with this type of statement. But then it was realized that this Gribov-Zwanziger theory has some infrared instabilities, and it favors the formation of condensates. And if you take into account the formation of these condensates, you get to what is called the refined Gribov-Zwanziger action. This was back in 2008. And you can just introduce these condensates effects by hand in order to effectively take them into account. And actually, this action, which takes into account the condensates, was re-derived using much more general algebraic arguments in 2013 and 14. So this refined Gribov-Zwanziger action has this form, is the standard gauge-fixed Yang-Mills action. The second line is the standard Gribov-Zwanziger modification, and the last line contains the gluon condensate contribution and also the condensate of the auxiliary localizing fields. So the localizing fields, they were introduced just to make the theory local, but as soon as they are introduced, they also have their own dynamics, and they can develop condensates themselves. So you have now these 2 parameters, little m squared and big M squared, that are fixed by their own gap equations. And it means that your tree-level gluon propagator now is has this form. So it's a bit different from the one that I presented before. And instead of going to 0 at k equals to 0, it goes to a finite value. And this is back in 2007 and 8, this is precisely what people from the lattice community started to see, that the gluon propagator actually does not go to 0, but goes to a finite value at very low momentum scale. Okay, now let me, after this very generic summary, let me make the statement about BRST symmetry, which is a very important symmetry in standard perturbative Yang-Mills theory. So it is a direct outcome of the Faddeev-Popov quantization, and the BRST transformations are given by these expressions here, and they relate fields with Gauss number G to fields with Gauss number G plus 1. And the gauge fixed action, of course, is not invariant under gauge transformations anymore, but is invariant under BRST transformations. And the S, which is the BRST operator, is a new potent operator, and it is widely used in proofs of renormalizability and unitarity in at the perturbative level in gauge theories. And what happens is that when you introduce the field space, the horizon in the field space, we can ask what happens with the BRST transformation and with the BRST symmetry. So if you apply now the BRST operator to the Gribov-Zwanziger action, for instance, you see that S of the Gribov-Zwanziger action is non-zero, but actually proportional to gamma squared, which is the Gribov parameter. This means that when you restrict the path integral to the Gribov horizon, you break explicitly BRST symmetry. But this breaking is what we call a soft breaking, because when you go to the ultraviolet, gamma goes to 0, and we recover BRST invariance. But in the non-perturbative regime, well, then this S is not does not generate a symmetry anymore. The fate of BRST symmetry in the non-perturbative regime is still under debate. But what I want to say is that it seems that introducing this horizon in the path integral, we are really, and therefore taking care of infinitesimal Gribov copies, it seems that we have a clash with BRST invariance. And of course, BRST is very important, for instance, to prove that correlation functions of gauge invariant operators are gauge parameter independent, for instance. So we want to understand whether it is possible to reconcile BRST with the Gribov horizon. And this is essentially, well, the way that we achieved that was by making use of dressed gauge fields. So we have a gauge invariant field AH, which is transverse, and it is obtained by the minimization of this functional along the gauge orbit. And when you minimize this along the gauge orbit, you obtain a very non-local expression for AH. But in the end, this is a gauge invariant object, and as a consequence, this is also BRST invariant. And now, having a gauge invariant quantity AH, we can rewrite the horizon function in terms of this dressed field. So you start with the horizon function in terms of A, you write it in terms of AH, and subtract all the junk that remains. And the junk that remains is always proportional to the divergence of A. So this is the main property here. So in the Landau gauge, you can reabsorb all this junk here this non-local junk, but with the proportion, the divergence of A being factored out, you can reabsorb that by a redefinition of the Lagrange multiplier that imposes the gauge condition. So you make this field redefinition, and this has a trivial Jacobian, and in the end, you have a horizon function that is fully dressed. So you replace the gauge fields by dressed gauge fields, and the Faddeev-Popov operator now is written in terms of dressed gauge invariant fields. And again, you can localize this theory because this is the horizon function and therefore non-local, by introducing the standard auxiliary fields that were introduced before. But you see now that we have AH, and AH, as expressed here, is highly non-local. So even after introducing phi and omega, which are the localizing fields in the standard Gribov-Zwanziger theory, we still have this non-locality coming from the dressed gauge field. But even at this non-local level, we can see that now, because of the introduction of this dressed field, the action is actually BRST invariant. So you can write S, you can apply S to SGZ, and this will vanish. So therefore, the introduction of this dressed field makes the theory BRST invariant. And as I said, it is connected to the BRST broken version by a field redefinition, and this is a special, let's say, case coming from the Landau gauge. So this is a property of Landau gauge. But this opens up the possibility to define a BRST quantization, and therefore go into different gauge conditions. But as I said, this action is still non-local. And one thing that the first consequence of that is that because you have BRST invariance again, you can see that if you take the derivative of the Gribov-Zwanziger action with respect to gamma squared, this is not an exact BRST variation. So the Gribov parameter is not like a gauge parameter, and therefore it can really appear in correlation functions of gauge invariant operators. In particular, the gap equation that fixes the Gribov parameter now is written in this form, which is manifestly gauge invariant. So the Gribov parameter will not depend on gauge parameters. And there is a nice story about that, which is we still want to make this theory local to apply standard QFT techniques. But also, actually, more recently, we also have been doing calculations with the non-local version. But the localization goes by treating the dressed gauge field in this form, where you have these H's that are introduced by exponentials of a local field, which is like a Stuckelberg field. So you introduce now this non-polynomial but local field, and you can localize the AH field by introducing now on top of the standard localizing fields these two terms. So when you solve or integrate out tau and eta bar and eta, you recover this action with the non-local AH. So this is a localization procedure. Of course, the action is not polynomial, but this is also encountered, for instance, in super Yang-Mills formulated in superspace, and so on. So with these enlarged field configurations, you have now many localizing fields, but just taking the BRST transformation. Yes, is there a question?
No, just to mention your, I see 10 slides to go. Unless it's for frightening us, you have 5 minutes left.
Okay, I will just be very brief in the 10 slides that I have.
Great, thanks.
So The action is invariant under these BRST transformations, and because of the property that I mentioned about field redefinition, correlation functions of gauge invariant operators computed with the BRST broken version or with this new BRST invariant version, they are the same. So this is so you can still do concrete calculations with the, let's say, more amenable version of the Gribov-Zwanziger action. So now I could spend some time explaining how to generalize the Gribov-Zwanziger action, for instance, to linear covariant gauges, where now you have an explicit gauge parameter that helps you to check whether your framework is consistent with gauge parameter independence. But instead of explaining the details, I will just say that now that you have a notion of BRST invariance within the Gribov horizon, we can define a BRST quantization. So a BRST quantization is just the standard, it corresponds to the standard gauge fixing action in linear covariant gauges. And on top of that, you introduce all the structure that restricts the theory to the region free of infinitesimal Gribov copies. This action that is non-polynomial is renormalizable, and this is a very hard proof actually, but it works. And now you define the theory to a class of linear covariant gauges. And again, you can proceed with the refinement of this theory. You see now that the condensate is formulated in terms of the dressed fields. So you are talking about really a gauge invariant composite operator here. And if you compute the propagator out of this action, you get very good agreement with the most recent lattice data for the gluon and ghost propagators, for instance. I just want to say that these dressed fields, they have a very special meaning in the Landau gauge, because these gauge invariant dressed fields, they essentially in the Landau gauge, they collapse to the gauge field itself. Of course, this is an on-shell statement, but it means that the Landau gauge plays a special role for this particular dressing that we are using. There are different dressings that will be, let's say, less nice in the Landau gauge, but that's why sometimes I call this the Landau dressing. But it means that you can do many things in Landau gauge, which is much simpler, and still get a meaningful results in different gauges by using these dressed gauge fields. We then generalized even further this refined Gribov-Zwanziger action. Now, even with gauge fixings that involve the Stuckeberg field that we used to localize the action, but I'll not enter these details, and because Joseph is not letting me to. But in the end, it means that correlation functions of gauge invariant local operators, irrespective of the complication of the gauge, you can always consistently compute them in Landau gauge with the standard BRST broken Gribov-Zwanziger action. So this gives the horizon, the Zwanziger's horizon function, an universal character, at least for covariant gauges. So just to close, let me make brief comments about gravity. And of course, in quantum gravity, if you treat quantum gravity as an ordinary quantum field theory, you're going to gauge fix. And again, you can ask about the existence of Gribov copies there. And for instance, if you choose Feynman, the bounded gauge, the copies equation, namely the zero mode equation, has this form. And now we also essentially, the use of the background field method is, well, it's essentially mandatory. So you have a Gribov copies equation that depends on the choice of background as well. So this is a very difficult equation to solve, but let's assume that you can solve as we did in the Landau gauge and find a region that is free of Gribov copies. This would be a background dependent region. So in gravity, the situation is much more subtle because you have to deal with the background structure. And in fact, if you break BRST, as we were discussing before, you also break background independence. So my expectation that if you try to deal with this problem in quantum gravity, just naively and break BRST symmetry, you're going to lose background independence for sure. So this suggests that we have to find also suitable dressed fields in quantum gravity in order to consistently remove Gribov copies. But this task was too difficult for me, and I started analyzing the problem in Yang-Mills theories. So I introduced the background structure in Yang-Mills theory and tried to understand how to deal with the Gribov problem within the background field method. And the result is that you have to, again, introduce a dressing. And now this dressing, it's a dressing that depends also on the background itself in such a way that in the end you have background independence. But it's very, very tricky and very, very subtle. And I don't claim that I still fully understand this in Yang-Mills theories, and therefore quantum gravity is still very far away. So in virtue of time, I will just thank you for your attention.